Okay, so last class we introduced this idea of dictionaries, right? And you read through the stuff, so you caught up on lists in the book and then read about dictionaries in the book and um, probably read some stuff that we may not cover necessarily in here. I might flip back to the book and just take a gander at what you looked at. But um, in any case, what we did right at the end of class last time is we kind of married lists and dictionaries together. So I made a reference to kind of an older language like C and said that dictionaries are kind of like structs in C. That is, they allow you to store a collection of name-value pairs where the values don't necessarily all have to be the same, like they do in lists. Okay. Um, in actuality, even lists in Python don't require the values to be the same, but for right now, let's just pretend they do. Okay. Um, so what we did last time is at the top here, I created this like global variable. So I just put it before everything else so we had access to it. And so we have a variable up here just called people. And this is going to be a list. And what we put in that list, as I just advertised, needs to be all like things. Okay, either a bunch of numbers or a bunch of strings, or in this case, a bunch of dictionaries. Okay, so then we wrote a little function here called add person. We decided we would represent a person as a first name, a last name, and an age. Okay, and what does add person do? Add person goes ahead and creates a blank dictionary, and then adds as under the variable first name. These are name value pairs. So the name is F name, the value is whatever was passed in for F name. The name is L name, the value is whatever was passed in for L name. The name is age, the value is whatever was passed in for age. All right. And then we ultimately append that person dictionary to this global list. That makes sense? All right. And we saw last time we went ahead and printed the empty list first. Then we added a person, Mike Littman, and this is my real age. And I was younger than that when I started teaching. I was 21 when I started teaching. But that ship has sailed. That was a couple of weeks ago. All right, so we went ahead and added that person, and then we went and printed this at the end of last class. And if you remember, we get our list-looking thing, and then we get what looked like a dictionary inside of that. Okay, we'll go ahead and run that real quick just as a reminder. Oh, well, there it is, right here. So here's our people. Okay, that's our empty list initially. Make this a little bit larger. Funny thing is, I can say I did that to help the people in the back, but I actually did that to help me see it. All right, so there's our empty list when we printed out people. Then we called our add person here, adding Mike Littman 23. And now we have a list with exactly one entry in it. That is the single entry in that list, which is a dictionary holding name value pairs. Okay, now I referenced this guy last class. We were talking about data representation languages a little bit. All right, and I mentioned that this guy, the format that we're looking at here is something that is called Json. Okay, JSON is JavaScript Object Notation. All right, so which means something to us a little bit since we're starting to transition towards writing our own objects. Right, so really what a dictionary is we can almost think of it as an object light. So a dictionary is an object that doesn't have functions built into it. All right, so it gives us all the storage capabilities, but not necessarily the do stuff capabilities, the abilities. Okay, so we went ahead and put a dictionary in there. Now I'm going to go ahead and let's just add a couple other people to this. We'll just use our add person thing here. So we'll go ahead and we'll add my brother. So we'll make sure we keep the ages relative, accurately relative. Let's go ahead and add a Van. Let's see if I can spell his name. I get that? Nailed it? All right. And you're What are you, 25? Is that real? You're actually 25? Man, I guessed at the last name there, and I guessed at the age, got them both right. I mean, I literally guessed at every character in this. So that was every single character in that name. All right. So now we got 3 people in there. We added each one, and we went ahead and appended it onto person. So if we run this again, we should now have 3 values in our list, each value being a dictionary, where that dictionary contains 3 name value pairs. Make sense? Okay. So now let's say that we were searching through our list. So we'll kind of, now we're going to go back to like last week when we talked about linear searches and then binary search with an insertion sort. So let's go back and let's say we wanted to do a search on our unsorted list, right? Maybe we're going to look for the first person whose age is 21. Just for no good reason. So we're going to search based on age. Okay. So we're going to go ahead and we're going to write a def find person. And this guy's going to take an age to search for. Okay, we'll just do this based on an exact age right now. Right, and what this guy is going to do is he's going to operate on this global variable. Now the reason I have made this global variable, which is different than what we've been doing before, is again towards that transition towards objects. When we actually write our own objects, we're going to have fields at the top here and then functions that do things relative to those fields. Right? I haven't quite introduced objects yet. I've introduced them. We're on the outskirts. Okay, so we've given ourselves effectively a global variable that all of these functions have access to, which is going to be like how an object will work. And then we've given ourselves the ability to represent name value pairs inside of these dictionaries. All right, so find person is going to assume the existence of this global list of dictionaries. And what we're going to do is we're going to go through that list, finding the first person in that list whose age is equal to age. Okay? Now, this is kind of taking our linear search one kind of logic step deeper, one layer deeper. All right? So we can use our normal loop that goes through every element of our list. So we can say for person in people, and I'll just go ahead for right now, I'll print out person. Okay, so we fill up our person list. We got 3 people in there. I won't print it out right here. Instead, we'll just go ahead and allow our find person to print it out, since right now that's all that guy does. Is he goes through our list just like any other list, and for each element in that list that we happen to name inside of a variable called person, we'll go ahead and print out that element, and we know that element is a dictionary. So now we'll get 1 dictionary per line instead of all of them strewed out in like that list, generic print a list format. Okay, so we'll go ahead and we'll call find person. Find person. And we'll type 21 in for right now, not a big deal. And I'm going to go ahead and get rid of our print people. We've been convinced that that is the empty list initially. All right, so we'll add some people, then we'll call find person, and we should just see the 3 people that we added, one line each, one on each line rather, proving to ourselves that our standard for loop will loop through a list, like it always has. It just happens to be that we have new kinds of animals that we're storing in our list now. All right, so there's our first dictionary. That's person the first time through the loop. Here's person the second time through the loop. Here's person the third time through that loop. Okay. Now, in this particular case, we happen to be looking for the person whose age is equal to 21, or in this case, the first person whose age is equal to 21 in the event we have more than one person. Okay. So we need to ask a question in here. So we're looping through all of our people. For each person we run into, we need to ask the question, is your age 21? All right, so we'll say if person at bucket age Okay, so this is how we get a value out of a dictionary. If that guy is equivalent to the age we're looking for, go ahead and return that person. Make sense? So if person at position age, so we don't index it based on numbers, we index it based on the names. For, we have name value pairs stored in there. Person at bucket age, if that's equivalent to the age we're looking for, go ahead and immediately end this function. That's what return does. And return the person we were just looking at, and that's a dictionary. Okay, and we'll go ahead and then print out the result of that. Proving in this case we should get Dave Lippman, because he's the one that was 21. Okay. Go ahead and run this. So there's our Dave Lippman. Okay. We search for 25. We should get Van. There's Van. Search for 23. We should get me. We search for 31. What's the result going to print out here based on your experience up to this point? None. Okay. Now, so the follow-up question is why does it print none? It's because nothing is actually ever returned. So it doesn't return none. It doesn't print out none here in the existence of 31. So let's just run this real quick so you see it. So there's our none. Okay. We never actually return anything. So this function ultimately boils down to nothing, because nothing was ever returned. So all this guy is doing is he is reporting back what was returned, which was literally nothing. It was a none value. Okay? That wasn't something we did. What we could do is we could come down here after the for loop and say, if we're still kicking, go ahead and maybe return the empty dictionary, something like that, saying we didn't find anybody. Okay? I'm not sure if that's necessarily any better than returning none. We could also maybe return a -1 not found, kind of have this guy work like our index of. Okay, this is actually a nice feature of loosely typed languages if we do it like this. In a strongly typed language like Java or C#, so in Java, the language we're going to use next semester when we're doing our Android programming stuff, because it's strongly typed, we have to specify the kind of value this function will return. If we intend for our function to return a value, we would have to tell it the kind of value it's going to return. So right off the bat, in this particular case, since we intend to return the dictionary associated with the person we found, we'd have to advertise up here in Java that this function returns a dictionary. Okay? Which then means we would not be allowed to return something like a -1 as a alternative. But in Python, anything goes. It's a loosely typed language. Okay? So I can certainly return a -1 here, and I can also return a dictionary. Either one of those is fine. We have the type inference engine, so when we actually work with the data, well, I'll kind of show you here by example. It's going to have to do some unpacking, which takes time. That's the whole relatively slow aspect of it. All right, so I'll go ahead and print out whatever find person 31 returns, which in this case should give us a -1. Okay, but that's our -1, not something that find person just boiled down to because we didn't do enough logic. So there's our -1. Now understand, this is both a when I did not have a return statement here, let me go ahead and get rid of that for a second. In a strongly typed language like Java, or really any strongly typed language, but I'm referencing Java since that's what we're going to be working on next semester, I would have had to say I'm returning a dictionary here. Now, not only am I only allowed to return a dictionary, I'm also required to return a dictionary. So two things that come with that responsibility. When I return something, it has to be of type dictionary, And because I advertised that was returning a value, I must return a value in Java. Okay? So as this is written right now, we saw it a few minutes ago give us a none because we never actually hit a return statement, right? That would not be allowed in a strongly typed language like Java. Now remember when we discussed Swift? So Apple's newest, latest, greatest language that tries to kind of look kind of like our web programming languages, but act like our high-level languages. Swift has introduced some things that sort of kind of let us pull off what we're trying to pull off here. They allow you to have a return type of something called any, which basically says anything goes. Okay. They also allow you to optionally have a return value. So you could put a little question mark there. So at first, when you come from a normal strongly typed programming background, there's a lot of extra little syntax in Swift that kind of bugs you. You got a lot of exclamation points and question marks you have to throw in there because you have these things called optionals where a function might return a value. And you have to advertise it as such. But what it does let you do is it allows you to pull off some of the logical trickery or whatever that we're doing here that usually has been reserved for loosely typed languages or web languages. Okay? So Java would not have allowed us to do something like this, returning a -1. Now that's okay, because what would Java do instead? We would say we're going to return some sort of object type, and in Java we would just return a null down here, which means we're returning nothing, and then externally when we go and use that value, we would ask the question, if it gave me null, that means it didn't give me an answer, therefore it wasn't found, something like that. So it's not like we've lost the ability to do the logic. We just have to do it in a different way. I might say a more structured way, because then you're guaranteeing the type that comes out of it. But so let's just look at this as an example. So we have our find person. If we find somebody, we'll return that dictionary. If we get through all the people, all the persons in people, then we'll ultimately return a -1 here. So down here, we can ask a question on this guy. We can say if find person return something other than -1. So if it's not equal to a -1, we can maybe do print person found or something like that. Else print not found. All right, so we can ask a question based on what's being returned from that guy. If it's anything but a -1, and would some dictionary be something other than a -1? If I look at a dictionary and I look at a -1, we can say those are different things. Okay, so this would be true for that, and we'll say, hey, we found the person. Otherwise, we'll say not found. So right now, our output should be not found, because we were searching for the 31. If we switch this back to 21, we should just get the generic found person, even though it did return that dictionary to us. This guy right here boiled down to a dictionary. We never stored it anywhere, so we don't have access to it anymore. Okay, if we wanted to give ourselves access, we could say something like result is equal to find person. And then we can check to see if result is not equal to -1. If it isn't, we can just print out result, the dictionary that was returned. That makes sense? Sometimes we want to preserve the value that was returned from a function. In fact, maybe most of the time, we want to preserve the value that was returned from a function. If we called the function, we were probably doing it for a reasonable reason. Every now and then, we might want to just use it to ask a question, but more often than not, we probably need the value at a later date. So I preserve the value here. We asked a question based on the value. Then we printed out either the result that was returned or just we converted the -1 to the verbiage not found. So there's our person that was returned for 21. That make sense? Okay. Now, what if we want to have another way of getting people into our into our list of people or array of people. So we've been introduced to what, the input function? Is it input or is it raw input for Python 3?
For 3 it's
Input, okay. So we'll say def add person, and we're going to go ahead and we're going to prompt them for some stuff. So we'll get that. We'll get a, say, fname is equal to input. Please enter a first name. And we'll say lname is equal to input. Please enter a last name. And then age is equal to input. Please enter an age. Okay. Then, so let's just start with that. So I'll go ahead and I'm just going to print out fname, print out lname, print out age. All right, so I have two separate functions here called add person. So I'll call my first version of that function the first 3 times, and then I'll call add person with no parameters. Okay, we want to see what this does. Add person takes 0 positional arguments, but 3 were given. So we tried to create 2 separate functions, sorry, these guys here, with the exact same name, but taking in a different number and or type of parameters. In strongly typed languages, this is allowed. Okay, it's an idea called polymorphism. Because this is an interpreted language and because of the nature of going through an interpreted language, we run into a problem outside of objects. We're going to re-explore this when we introduce objects. Having 2 functions with the same name. So we're going to change this guy. We're going to say add person from user. Okay? So we'll name that guy something different. So there's our add person from user. Run this guy. Please enter our first name. We'll call this guy Clark Smith, and he's going to be 34, let's say. All right. So there's it proving to us that we read in those 3 pieces of information. All right. Now, I ultimately, if I'm inside of add person from user, I ultimately would like to add this person to my people list. How do I do that? Call the other function. I mean, I could certainly recreate this logic, right? I can create an empty dictionary. I can load in first name, last name, and age into that dictionary and say, okay, well, that's good. But I've already written that logic. I already have the ability, given a first name, an L name, and an age, to throw something into my people list. So I'll just come in here, and we're going to call this guy add person. We need to type it way better than that. All right. Okay. So add person. We're going to pass it the F name, the L name, and the age that we read in. And then just to test that, I'm going to actually search for 34. So I'll make sure I put that age in again for that last person. All right, so it's going to ask me again each time I run this program, because right now our programs don't know how to persist between runs, right? They don't know how to keep track of our people list between runs of the program. That's something that we maybe take for granted, right? You know, when you run applications on your computer, you kind of rely on them loading back up where they left off last time, or remembering, you know, a whole bunch of stuff you've entered in. You know, because a lot of times you don't sit down and write a 5-page paper in one sitting, right? or well, maybe some of you do when you're waiting until the morning of to write the 5-page paper. But you know, in any case, most of our computer programs today, we rely on them remembering stuff between runs, and we haven't even introduced that yet. Okay, so we'll go ahead and add the 3 people. Get the 4th one from the user. I'll make sure I make his age 34, and then we should see that that guy was successfully added. Ooh, interesting. So, what happened here? We got a not found. I'm just going to show you something real quick before we call this. I'm going to go ahead and I'm going to print people. I'm going to print people. Now, I want you to pay close attention to the, before I say this, anybody have a suggestion of what might have gone wrong there? We definitely entered in Clark Smith, age 34, right? Then we searched for 34, and it did not find it. It worked for all the other ages. Is 34 some sort of magical dead number? We're going to go with that. Okay. Any suggestions? Let's go ahead and run it. We're going to still see not found again down here, but before that, we're going to print out our 4 things in people. Okay? And when we see that up there, I want you to look at the 4 different dictionary entries. So analyze them closely. Anybody have a theory now? Go ahead.
The 34 for Clark is a string instead of a number.
Yeah. All the other ones, when we entered it ourselves, we gave it as a number. But when we read it in from the user, we expected a number from the user. You know, as a person, we expected them to give us a number. But when we use the input function, it reads it in as a string. But it just so happens we have a couple of converter functions, right? How do I turn a string representation of a number into a number? The int function, yep. Now, we're going to rely on the person giving us an actual age instead of, you know, putting in like the word cat for their age or something like that. So let's not do too much error checking here. But so now what we'll do is up here, when we read in age, we'll go ahead, I mean, I could wrap this whole input thing inside of that int function, but let's go ahead and just capture it as a string and then convert it to an int here. That make sense? So we'll have it in our variable age as a string initially, and then we'll go ahead and when we pass it to add person, we'll give add person the integer version of that guy. Let's go ahead and run this again. Okay, notice it did find him that time, and notice that his age is now not a string, it's a number. That make sense? Okay, so I'm going to go ahead and let's add, I'm going to kind of get this set up for your guys' homework assignment. But so I'm going to take away the add person from user. It's a function that we have available to us now, but we're not going to use it. And I'm going to add some more persons here with some different okay, and let's do some ages here. So we had a 34, we have an 18, We have a 29. Should be good enough. Okay. So, what if I wanted to take my list of persons and sort them on age? How would you go about doing that? Right off the bat, those of you who use the built-in sort function are going to be sorely disappointed that it's not going to just randomly work on any dictionary. Okay, it worked on numbers, it worked on primitive type values that had a sense, but in this case, I'm saying is if I use the built-in sort function, not the one we might write or the one we will write, it's going to say is the dictionary created from this guy less than the dictionary created from this guy. What does it mean for one dictionary to be less than another? It doesn't really make sense, right? We don't know what answer we should be getting out of that. In this particular case, we're deciding we're going to compare dictionaries specifically on their age value. Okay? So what sort do we know how to write? We know how to write insertion sort. Could we modify our insertion sort for sorting a list of dictionaries instead of a list of numbers? How hard would that be? Not that bad. Well, so let's look at this guy. So we'll do our def insertion sort. And, well, we know that we already have global access to our list, right? So we don't actually pass this guy anything, because he knows about the list that we have up above. All right. Now, remember with insertion sort, we start at the bucket 1 of our list, and we bubble things towards the beginning as far as we can get them, right? Okay. Is my keynote back up yet? And then we have that follower, all that stuff. Oh, let's see. All right, so here was our insertion sort. So we had our current start position that started at bucket 1, then 2, then 3, then 4. Okay. We had the follower that would get reset to that value each time and then would follow, in this case, our dictionary back towards the beginning as we swapped it towards the beginning as far as it could go, right? We used why did we need a swap helper? Remind me, what was that guy for? Okay, because if we have two values in our list, in this case, we have 2 buckets, both of them hold dictionaries. If I overwrite this bucket with this dictionary and I don't preserve this guy first, I've lost that value. So I need to take this guy, store him here, this guy, put him here, then this guy, put him here. Okay? So those are the variables we're going to need to pull this off. So first, we're going to need a loop that's going to go through all the buckets between bucket 1 and the last legal bucket in our list inclusive, right? So we're going to use the range function to give us a list of numbers. Okay, so we're going to say for, and let's use the variable name we had here. So cur start pos in range of 1 to length of people. And this is going to be non-inclusive by default, correct? And we can use the default step of 1, so we don't need to give it that third parameter in our range function. Okay. Each time through, we're going to reset the follower. So the follower is equal to cur start pos. So whatever that guy is. And then we're going to bubble the current number towards the beginning of the list as far as it can go until the age of the follower is not less than the age of the follower minus 1. Okay? So we want to make sure that the follower is not currently at bucket 0. So that means we're at the beginning of the list and there's nothing before us. So while the follower is not equal to 0, so or you can say it's greater than 0. Either one of those is reasonable. Okay. And we want to ask the question, is the age, is the value of age at the current dictionary, the dictionary associated with the follower, is it less than the age of the guy before me? How do I write that? How do I ask the question? How do I write the Boolean expression that says, is the age of the follower less than the age of the follower minus 1? Or the dictionary at bucket, the follower. It's the same question we asked before, but it feels a little bit more cryptic now, right? Now we're accessing things at a particular bucket. How do I get the dictionary at position the follower, as well as the dictionary at position the follower minus 1? So how do I get just access to the dictionary at bucket the follower? How would I access if our array was called people and it was a list of numbers? How would I get the number at position the follower? Yeah, people at the follower. People square bracket the follower. How do I get the dictionary at position the follower? What do you think, Ali?
What's the dictionary called?
Well, our list of dictionaries is called people.
Right.
The dictionary is just, it's a list of dictionaries. Our dictionaries don't have individual names. By the way, you're playing into my trap perfectly. Yeah. You've been just a great contestant. It's identical. A list of stuff, whether it's a list of numbers, a list of dictionaries, a list of objects. If we want whatever's in the list at bucket the follower, we just say list square bracket the follower. That's it. Okay? But the second we start putting more complex data into our list, it gets intimidating, right? We start second guessing ourselves, like, oh, it's got to be harder than this, right? Well, all we say here is, I'm going to start off by saying something, and then we'll give you another chance to be wrong. Sound good? Okay. So we'll say people at bucket the follower, and ultimately I'm going to write this in an incorrect way, and you can help me fix it. Is less than people at bucket the follower minus 1. Okay. So all we really need to worry about is what's after the and here. So this part right here. So here's my list. It's called people. People at bucket the follower. This guy right here, what kind of animal will that be? Cat, dog, or dictionary? It's a dictionary. Okay, that guy's going to be a dictionary. People at bucket the follower minus 1. What kind of animal will that be? Also a dictionary. Okay. Now, I don't actually want to ask the question, is this dictionary less than this dictionary? I want to ask the question, is the age attribute of this dictionary less than the age attribute of this dictionary? How do I do that? Do the what? Okay, so bucket, like that? Is that not what you were saying? Is that what you want to say? You don't get to know that yet. down here when I printed result, I'm going to go ahead and I'm going to print result at bucket H. So we know find person returns us a dictionary, right? Can I get the age of that person like that? That's how it went in, isn't it? Okay, so person at bucket age. So instead of a number, instead of bucket 1 or bucket 2, bucket 3, it's bucket age. These are name value pairs. So I can say result at bucket age, and that'll give me the result. For right now, I'm going to just take out this line so you can see this work. I'll put it back. So we're not actually calling our insertion sort yet. Okay. We got it 50 or 55? 55. Okay, good. All right, so we'll go ahead and run this. We expect for age 34 to get, well, actually, instead of age, let's do L name. Because we're searching for age 34. So we expect to get the person whose last name is Smith, correct? All right, so we should see Smith get printed out here. So there's our Smith. All right, so now we've seen how we can access a specific attribute of a specific dictionary. Okay, so result was a dictionary. If I wanted to get the last name attribute, the L name attribute of that dictionary, I treated it kind of like a list, but I gave it the name of the attribute I wanted. Because one thing you cannot guarantee is in a dictionary that order is not guaranteed. You don't necessarily know that first name comes before last name comes before age in the internal structure of the dictionary. We're trusting the dictionary is set up correctly. Okay? So when we want the L name, we just say, give me the L name, however you have to do that. So we just saw this work. And we know that this guy right here is a dictionary. And that's no different than what we had up here. We know that this guy is a dictionary, correct? And if that guy boils down to a dictionary, is this the way we get the age attribute of that dictionary? Yeah. Okay. It looks a little bit cryptic because when you're looking at this, you're just like, oh, wait, there's way too many square brackets here, right? But once you actually break it down, you say, you know what? This guy ultimately becomes a dictionary. This is the same thing as down below where I said result. And I'm asking for that dictionary's age attribute. So if this particular dictionary's age attribute is less than the dictionary before him the age attribute, then we need to do a swap, correct? And then the follower follows. Okay, our variable name for our swap was swap helper. So we're going to say swap helper is going to equal people at bucket the follower. Do we want the follower or do we want the follower at position H? What am I swapping here? Am I swapping just ages or am I swapping the entire dictionaries? The entire dictionary. So I'm going to preserve the dictionary at position the follower. Then I'll overwrite that list at position the follower with the follower minus 1. Then I'll overwrite the follower minus 1 with my preserved dictionary. And then the follower follows. Make sense? All right. So initially we're putting them in out of order. We'll print people. I'll go ahead and just get rid of this stuff for right now. Then we'll call insertion sort passing it no parameters because people is a global variable, so insertion sort already knows about the list that we want to sort. And then I'll go ahead and print people out again. And we notice a second time we have 18, 21, 23, 25, 29, 34. So it's not sorted the first time, is sorted the second time. Make sense? And if you go back and you look at the algorithm we wrote previously for insertion sort, it's going to look almost identical to this, right? The only place things get a little bit hairy is right here. Because I'm taking one deeper step in, because my values that are in my list called people are not simple values anymore. Now they're dictionaries. And I'm choosing to sort this list on age. Make sense?
So what would it do if you didn't specify age?
I think it would probably compare the memory addresses of those dictionaries. Treat them as hexadecimal values, and so nothing logical, nothing that means anything to us. Now, for our homework, we're going to create a binary search for age. So this is going to be pretty similar to find person. So we can even say find person binary search or something like that. Okay, and this guy should return a person whose age is equal whatever to age, or a -1 if it was not found. That makes sense? So you're going to modify your binary search algorithm to work on this sorted list of dictionaries. It's not going to be a huge jump, okay? But you're going to have to, when you do your comparison, should it be to the left or should it be to the right, you're going to have to make sure you dig in and get the age value for that dictionary, not the dictionary itself. Questions, comments, concerns, bribes? All right, I will see everybody on Friday. I'll go ahead and post this code up on Slack and put the assignment up.